So today I want to continue with the periodic table. This is basically what we did last time. And I want to talk about something called an ion and also isotopes. Those are the two main focal points for today. So just as a quick review, we've got most of the periodic table are metals, and they form positive cations. So everything labeled in this category here, those are metals. The opposite of metal is a non-metal over here. Now, frequently we're going to find that metals like to hook up with non-metals to form an ionic compound like sodium chloride, for example. And then these in-between guys that lie along the squiggly line here, those are called metalloids. And metalloids can either act like a metal or a non-metal depending on the voltage applied to them. And that's the basis of a transistor. Okay, and those were invented in this country in the about 1947 and by AT&T. Okay, so let's now talk about, and as the elements appear on the periodic table, they are neutral, no charge. Now, there are two charged particles in every atom, no exceptions. There are protons and electrons, and those charges are opposite, but equal. So if the element is neutral, that means the number of electrons equals the number of protons, no exceptions. And I like about the no exceptions. Okay. Let's see here. This I think is from last semester. The one we didn't have as much information on. Okay. So a neutral atom, the number of protons equals the number of electrons. Now we're going to fill out a table in a little while. Okay, well, what if the number of protons does not equal the number of electrons? Then we have something called an ion. That means an ion has a charge because those are not equal. And the charge depends on which is more, the protons or the electrons. So if the protons are more, we have more positive charges than neutral, or we have more positive charges than negative charges, then the net overall charge in that ion is positive. And the fancy name for that is called a cation. This name is derived from electrochemistry inside of an electro cell, similar to inside of a battery. And those positive cations are attracted to the cathode within that electric cell. Don't write that down. That's just where the name is derived from. The easy way to remember this is think of the T looks like a positive. Okay? Okay, if the number of protons are less than the number of electrons, we have a net negative charge. and it's called an anion. And those within the battery are attracted to the anode. That's where the AN comes from. Okay, the N, think of the N as negative. I'm trying to remember between the two. Okay, so that's an ion. There's another type of elements called an isotope. Now, an isotope like carbon-14 and carbon-12 are isotopes of one another. The C is the same, though. That means the chemistry of C14 and C12 is the same. What's the difference then? The difference is the number of neutrons. So isotopes differ in the number of neutrons. So to figure out how many neutrons carbon-14 has versus carbon-12 is to figure out how many protons. Okay, yeah. Very good question. Neutrons don't affect the chemistry except for something like that involves mass. The chemistry is in the electrons. So if the number of electrons is the same, which it is between carbon-12 and 14, then the chemistry is the same. What's different between isotopes is one's heavier than the other. So if you were running something like a mass spectrophotometry experiment, you could actually separate out the isotopes because that is sensitive to mass. Yeah. The ions? Yes. Yeah. Because again, electrons where the chemistry is. And ions is different in the number of electrons. So if you have an ion that's different than another ion, even though it's carbon or sulfur or whatever, chemistry is going to be different. So yeah, good question. Yeah. The only properties are mass related. Chemistry wise, it's the same because the number of electrons isn't affected by an isotope, only the number of neutrons and hence the mass. And neutrons have no charge. So you can load them up. Now, what's interesting about neutrons, when you get into nuclear chemistry, inside of a neutron are two particles, a proton and an electron inside the neutron. And that's why it has no charge because they cancel each other out. So a lot of people say, well, electrons are on the outside of the nucleus. No, incorrect statement. There's electrons inside the nucleus, buried inside neutrons. So there's electrons on the outside the nucleus and inside the nucleus. And whenever we have nuclear decay, easier for me to say, I have a hair on my dogs don't shed, yet I have a hair on my, maybe it's my hair. It's pretty wild stuff. So when something decays, like radiation, an atomic blast or something like that, you have all kinds of elements changing from one to the other because inside those neutrons, electrons are shooting out. That means you gain a proton. Protons determine what element it is. So in an atomic bomb, for example, we make calcium and we make krypton because the number of protons from the original uranium has changed. So it's pretty wild what's going on here. But isotopes, chemistry is the same, unless you're dealing with a process that's mass sensitive. Like when they purify uranium, for example, there's two isotopes uranium, U-235, U-238. U-238 is the most common one. U-235 is the one you can make bombs with, and nuclear reactors, all that kind of stuff. So they separate the two by mass. That's what Iran is in the middle of doing. North Korea, we've been doing it since 1942-ish. Russia's been doing it. And we separate that uranium. Uranium is very popular in the United States. It's very easy to get uranium in the Southwest. In fact, if you buy pottery in Arizona roadside stand, the chances of it being radioactive is very high because uranium is yellow in color and they use it to make a glaze for their pottery. And up in Tacoma, we had a whole bunch of pottery that was radioactive. Take a Geiger counter over it and it goes crazy. And they always warn you at the airport, don't buy pottery side of the road. So what happens at these plants is they run it through a centrifuge, and the heavier stuff will spin out farther than the lighter stuff. The heavier stuff is uranium-238, the lighter stuff is a 235. U-235 is about 0.05%. Not very much. But boy, when you get it, you can do lots of stuff with it. Good and bad, like most things in the world. Pros and cons, good and bad, all that stuff. So anyway, that would be an example of where the isotope matters a lot in the separation. So sorry for the long-winded answer. Okay, any questions about that? I used to teach nuclear chemistry to my intro class up in Tacoma, and when we talked about energy, and they learned about how a nuclear power plant works, how a nuclear bomb works, all kinds of really interesting stuff. It's pretty cool. It's what the alchemists strived to do back in the 1400s. Okay, so let's delve into carbon-14 and carbon-12. How do you know how many neutrons does carbon-14 have? Well, carbon-14, the 14 that means there are 14 total particles. Protons plus neutrons. So if we know how many protons there are, we can find out how many neutrons there are. So I need to know how many protons there are. Okay, this is a nice segue back over our periodic table. And for each element in the periodic table, there's a little box. Depends on the periodic table. The one I give you has the name there. The official one for this department, when you get out of this class, not going to have the names there. It's going to look more like that up there. Okay, all periodic tables have at least the symbol and two numbers. There's a decimal number and a integer. The integer says how many protons does carbon have? 6. It's also called the atomic number. So the number of protons and the atomic number are one and the same. No exceptions. The decimal number on the bottom is the average of all the isotopes on our, well, I was about to say on our world, basically in the universe, but mainly on this planet. So that means there's carbon-14, there's carbon-13, carbon-12, carbon-11, etc. Average all those masses together, and you get 12.01. Now, because that's closest to carbon-12, that means the most common isotope for carbon is carbon-12. But anyway, that's what the decimal number is. Again, that's the average of all the isotopes. Now let's go back over here. So carbon-14 then has 6 protons, because its atomic number is 6. And how many neutrons? Now this is all the math in unit 2, is subtraction of whole numbers. So how many neutrons? 6 plus what is 14? 8. So carbon 14 has 8 neutrons. Carbon 12. 6 neutrons. So that's the difference between carbon 14 and carbon 12, 2 neutrons. And because carbon 12 and carbon 14 is neutral, that means both of them have 6 electrons. But when you name the isotope, it's based on protons and neutrons, not the number of electrons. That comes into play when we talk about the ions. Okay, so does that make sense? Okay, so we've got what is an ion? It's a neutral atom. There's one more thing I want to talk about before we get into this worksheet. Whenever we write an element, like carbon 12, we write the symbol. On the bottom of the left-hand side, we write the number of protons. Up here, that's the isotope name, carbon 14. Oh, I guess we're talking about carbon 12 here. Let's do this. So this is P plus N. Now this applies whether it's a neutral atom or an ion. For example, if this was a +2 ion, we'd write C +2, 12, 6. Now, what's unfortunate is the periodic table has these two numbers reversed. Remember, we just looked at the carbon on the periodic table. So for the periodic table, the number of protons is on the top, not the bottom. But it's only for the periodic table. Everything else, it's protons are on the bottom. Okay, so now we know how to determine an isotope. Protons plus neutrons. We know what an ion is. So we need to practice this. Oh, one more thing. The periodicity of the periodic table has some very nice things to say. One is the charge that the elements do. In the first group, the alkali metals, they all form a charge of +1. So everything in this column number 1 forms a +1 charge. Now, hydrogen is weird. Hydrogen can go there on the right or on the left. It depends whether it's an acid or not. So hydrogen is goofy. It only has 1 electron, so it can easily gain 1 or lose 1. And that's why it kind of flip-flops between the left and the right side. Everything else below hydrogen is always +1. Why do you think it forms a +1 ion? Just in general. If in doubt, what do you say? Is this more stable? So a +1 lithium is more stable than a 0 lithium. In other words, if you went out in nature and tried to find lithium metal, you would be looking for a long time. To find lithium ion, it's very easy to find because the lithium ion is more stable. So just if in doubt, more stable. It's a very safe statement. And I say this to all my classes, regardless of the level. When I'm in the midst of organic, talking about mechanisms and stuff, it's all driven by stability. And then when you get into more advanced chemistry, you talk about, you can actually calculate and put a number on stability. It's called Gibbs free energy. And whether it's stable or not by the Gibbs free energy number. So our class, because it's more stable. Okay. And then this goes across +1, +2, +3. Carbon group, because it's either a +4 or, as you'll see in a second, a -4. So if we go to the right, underneath fluorine, it's a -1, and it goes -2, -3, and -4. And carbon is that place where it either loses 4 electrons or gains 4 electrons. So carbon does neither. Carbon doesn't form an ion. Carbon group now I'm talking about. Okay, so again, we're seeing a lot of nice things about the periodic table. And we're going to continue to study the periodic table throughout the semester. Okay, so let's practice this stuff now. All right. This worksheet is in Canvas files. Let's make sure it's in Unit 2. Okay, it's these two right here. This guy and this guy. Protons, neutrons, electrons. There's a neutral one and an ionic one. Okay, so that's what this is here. Okay, so what we're going to do is we're going to fill in the name. I'm going to put the atomic symbol here. We're talking about what's the atomic number of protons, neutrons, electrons, atomic mass. So this worksheet assumes that we're talking about neutral atoms. That means electrons, there's no charge, so electrons equals protons. So these two are always equal if it's neutral. If it's ionic, they're never equal. These two are also always equal. And the isotope is P plus N. So we have a P and an N. Okay, so let's do some of these. Now you're going to have a chart like this on your test too, both ionic and neutral. Okay, first thing is Let's find B on the periodic table. Okay, B is at the top, kind of just right of center, the very top. Boron. Now, if you look on your periodic table from your lab packet, it included the name of all those symbols. Okay, so we know it's boron. We need to find out what isotope it is, though. Okay, and one other thing, this is an integer. Always. No exceptions. Because we're counting particles, not parts of particles. And that's what a decimal will give you, is parts of particles. Okay. Well, boron, if you look on the periodic table, how many protons does boron have? 5. So its atomic number is 5. How many electrons does neutral boron have? 5, right. Remember, charge is 0. So charged particle proton, charged particle electron, they have to be equal, otherwise it's not 0. All right, so what's the atomic mass? What's the isotope number for boron with these numbers? Huh? No. 10.81 is a decimal. Remember, it's got to be an integer. So 11. P plus N. Protons 5, 6 neutrons. So that is boron 11. See where the 11 is up there? 5 protons, 11 P plus N. 11 protons and neutrons. Let's do one more, then I want you guys to practice this. Let's I don't know. Let's do this one here. 29. Okay, 29 is copper up there. Okay, well, you don't know what isotope number it is yet. All right. What's the symbol for copper? Big uppercase C, lowercase u. Whenever there are 2 letters in the symbol, the first one has to be uppercase. The second one has to be lowercase. No exceptions. One of the reasons is cobalt, symbol for cobalt is CO. The symbol for carbon monoxide is CO also. So how can you tell the difference? Cobalt has got a lowercase O in it. Uppercase O is oxygen. Uppercase C is carbon. So CO can either be cobalt or carbon monoxide. Cobalt has the lowercase O in it. Okay. So it's copper, and atomic number is 29. So that automatically makes it 29 protons. All right. I told you it's got 35 neutrons. So what is the atomic mass of the isotope? 29 plus 35 is 64. P plus N. Now this is a neutral copper, so how many electrons does it have? P and E are equal if it's a neutral atom. Okay, so now we can write our symbol now. Okay, so it's got 64 for the isotope. It goes on top. And it's got 29 protons. So that chemical is copper 64. So what I want you to do is practice this right now. Why don't you do at least down to copper? Now on the test, I could ask you questions like, how many total particles are in copper 64? How would you answer that question? Well, we know protons is 29. We know neutrons is 35. So how many total particles are there? Huh? 900? 9 to the, you said 93? How'd you get that? Exactly. You included electrons, right? Most people say 64. But when I say particles, electron is a particle, proton's a particle, neutron's a particle. All three count. Good. All right, so go ahead and work on these guys. I'll wander around. We're going to have a similar table for ions next. Ions are trickier than neutral. And for those of you who came in late, if you did not do your take-home problem on the test, you may still get partial credit for it if you do it tonight, maybe by midnight. And get it correct, by the way. That is a good use of highlighters. Don't forget, these are blue down here too.
Yeah.
That was quick. This makes sense? You're not saying yes. Is this reasonable?
Yes.
Okay. This making sense? Ions are a little trickier. They're the P and the E's don't match, which makes, then you have a charge. You have to figure out what the charge is. Yeah, this is, if you don't know this, you can't do the other. So this making sense? There are a whole bunch of pins on your purse.
Huh? Yes.
Cool. It's making sense? Makes sense. It didn't flicker once. They must have actually fixed it.
Doing the second one.
Okay, so these, oops, sorry. These two are always equal, even if it's an ion or neutral, are always equal. So I usually give you, sometimes I give you just that, and then that will tell you, based on here, how many protons, and then that's automatically atomic numbers. Sometimes they abbreviate atomic numbers Z. Okay, there's three parts to that. Protons, neutrons, and the sum. And I have to give you two of those to find the third one. So it's going to be protons and neutrons and these three together. So you have to have two of those to get the third one.
This is 23.
Hmm?
Isn't that really positive?
No, don't go by the decimal number, ever. Because this is the average of all these.
So it's basically 20. Because it's 22.99, but you round it up.
That's the most common one, but you don't round the decimal numbers. You calculate protons and neutrons. That's what determines the isotope. This is the average of all the isotopes. So this isotope may not be that plentiful. I just made these numbers up, except for the protons, but on the neutron, I just made those up. So they don't correspond at all periodic table. So you don't use a periodic table except for the number of protons to calculate this. And then I have to give you either the neutrons and protons or the atomic mass and neutrons, but three variables, got to have two to solve the third one. Okay, that's right. So it's going to be 11 plus what is 24?
Okay. Oh, I did say 24. I'm so stupid. Because protons plus neutrons were literally, I told you to read that. Yeah, I thought myself. Yeah. You're so dumb. It clicked when you
And so no decimals over here. Because this says how many particles. You can't have a part of a particle. And if you put a decimal there, you're insinuating it's part of a particle.
So smart. I figured that out by herself, totally.
You guys are fine. And these are the answers, by the way. Okay, so let's jump into ions now. Okay, so we have a very similar looking table for ions. Okay, so remember now, ions, protons does not equal electrons. And the charge is going to be whatever there's most of. Okay, so now the elements are all the same, it's just that these are all ions. So electrons are going to be trickier than before. Before, the electrons always equal the protons because the charge is neutral. Now they're not. Okay, so boron. Boron's got 5 protons. Atomic mass is going to be 11. Atomic number is 5. And the name is going to be boron 11. Okay, now the charge. Charge is 3 plus. Now, if you know the charge, you can calculate the electrons. 3 plus means there are 3 extra positive charges. That means there are 3 extra protons, as protons are positively charged. Okay, so how do we find the number of electrons? Protons can never change. If you change protons, you change elements. So protons are static. It's always, boron will always have 5 protons, period, no exceptions. If it's got 6 protons, it's going to be carbon. If it's got less, it's going to be beryllium. It's got to have 5. So the only one we can change are electrons. So 5 plus what gives us 3? Five minus 3 is 2. More of that advanced math. So you look at this, and you look at the charge, and they have to be equal to that. And electrons are charged as negative. Protons are positive. So when we combine electrons and protons, they have to be equal to the charge. So 5 minus 2 is 3. The 5 is positive. That means it's going to be a positive 3. Okay, that's the only difference in this table versus the other one, is the electrons are going to be, and the charge, or the two things are going to be different. Okay, so any questions so far? Isotopes are the same, P plus N. The name is the same. Charge and electrons. Okay, so let's go down to copper again. Okay, atomic number, protons. Okay, I gave you electrons and I gave you protons. So what's the charge? Positive or negative? The two parts correct, but is it positive or negative? Positive. Because there are more protons than electrons, hence it's positive. So you take the difference and see which one is more, P or E. Okay. What was the atomic mass? It was 64, right? Yeah, 64. Okay. Notice there's no charge reflected when you name it. Copper 64. There's no charge implied there. But we do know it's a metal, and metals always form plus charges. Because why? Because it's more stable. That's why they form positive charges. Okay, so what I want you to practice this right now to the end. Okay? If you got it down pat, we're done for today. Otherwise, I want to give you guys some time to practice while I'm here, roam around. Are there any questions on the charges? Yeah. We're going to get into that a little bit. I can't go too far because of the scope of this class, but there's a way to figure out that charge, because certain charges are more stable than other charges. So, for example, copper always forms a +2 charge in nature. Why? Because it's more stable than the +1 and the +3 and all that stuff. So once we get into the electronic configuration of the electrons themselves, you can start to see some trends and why one is more stable than the other. But in this table, I just randomly chose those. There's no form as to the number of electrons I chose for this table. I did this like 20 years ago, this table. Yeah, you had a question? Oh. Interesting, you had the same question. I covered that in 1A in depth. And most people cover it in 1B. And it naturally comes up in 1A or 3B. One of the two. Okay, I'm going to end this recording and get this video to render. Okay, I'm going to stop the share for a second so I can stop the recording.